Okay, so let's start building synchronous counters. So synchronous counters are going to be counters that, unlike ripple counters, all the flip-flops or all the clocked elements are going to have the same clock signal. And in a synchronous counter, I will proceed in the same fashion. So I will use the same methodology regardless of whether my counter is a natural or non-natural mod number. And this differs from a ripple counter. So for a ripple counter where it was a natural modulus number, I had to wire it a certain way. But when it was a non-natural modulus number, then I had to include this logic circuit that would asynchronously reset the counter at the first invalid state. And it turns out with synchronous counters, I don't have to make that distinction. Now, the advantage of a synchronous counter, as we're going to see, is that I don't have this problem of propagation of or cumulative propagation delay like I do in a ripple counter. But the disadvantage, of course, is that it is slightly more complex than a ripple counter, and it takes a little bit more work to create. So let's go through the steps one by one. So the example that we'll do, I mean, we'll start with a natural modulus number just to show you, but it doesn't really make a difference. And afterwards, we'll progress to other modulus number counters. So we're going to do a mod 8. So if you recall, for a mod 8 counter, I have to have 3 bits to express a mod 8 counter, right? I'm going from 0 to 7. I need 3 bits, which also means I need 3 flip-flops. And I'm going to draw the state transition diagram. Then I put bubbles around all my states. So my states are simply my counter outputs. And I'm going to do an up counter in this example, but it's exactly the same strategy as for a down counter. And we're going to see that. And that, again, also is unlike ripple counters where I had to wire up my ripple counter differently depending on whether I was wiring an up counter or a down counter. But let's make it a standard mod 8 up counter, and let's just see how it differs. So again, my arrows are just transitions that occur on the clock edge. So these are synchronous transitions. And this is my state transition diagram. Okay, now the next thing I need to do is I need to write what's called an excitation table. So an excitation table is kind of like a truth table, but with some important distinctions. So I start off by writing out all possible present states. So present states are the present values of Q2, Q1, Q0. And in a mod 8 counter, I can have 8 of them ranging from 0 to 7. And then I'm going to write out what the next state is going to be after the transition. And I'll represent the next state with this plus, this little plus superscript on top of my Q's. So what do I mean by that? If my present state is 0, I want my next state simply to be 1, right? So let's write that. My next state should be 1. And if my present state is 1, well, I want my next state to be 2. And how do I know this? I mean, I can read it directly off the state transition diagram over here, right? It's actually pretty easy once I have the state transition diagram. If my present state is 1, then my next state should be 2. And if my present state is 2, my next state should be 3. So let's write that out. And if my present state is 3, then my next state should be 4. So that's what this line says. This line says that if my present state is 3, my next state should be 4. And similarly, if my present state is 4, my next state should be 5, right? This is an up counter. And you can see already how versatile this is going to be, right? Because nothing is restricting me to saying that my next state should be an increment of my present state. I can go in any order I want. So I can have any counting sequence that I want. And what happens over here at state 7? What's my next state? So here I am in state 7. I can just read it directly off the state transition diagram. And I see that my next state is going to be 0. So I'm going to write that. Okay, so now what's the next thing I do? So the next thing I do is I need to know what my control input should be to get me from my present state to my next state over here. And this, of course, depends on which type of flip-flop that I'm using. So if I'm using a D flip-flop, my control inputs will be D2, D1, and D0. But if I'm using a JK flip-flop, then my control inputs will be J1 and K1. Actually, sorry, I should have started with 2. So J2 and K2, J1 and K1, and J0 and K0. But for simplicity, let's just use a D flip-flop. So if I'm using D flip-flops, my control inputs are the synchronous control inputs to all 3 of my flip-flops corresponding to Q2, or here Q2, Q1, and Q0. And those control inputs are D2, D1, and D0. So recall that for a D flip-flop, in order to, here, why don't we just write out the truth table for a D flip-flop? So for a D flip-flop, so this is the excitation table. So the excitation table for a D flip-flop is this. So what are my possibilities? My possibilities are that my present state is Q, and I want my next state, my present state Q is 0, sorry, and my next state, I want it to be also a 0. Or I could say that my present state, my present Q output, but I want my next state to be 1. I want my next Q output to be 1. Or I could say that my present Q output is 1, but I want the next Q output to be 0. And finally, I can say that my present output Q is 1, and I want my next output Q to be 1. And what should D be in all of these cases? Well, we know that to get the next state equal to 0, it actually doesn't really matter what the present state is. It doesn't matter what's here. What only matters is what I want the next state to be, because in a D flip-flop, Q, the output, will just follow the value of D at the clock edge. So if I want Q, or next state Q, to be a 0, then D just has to be 0. And if I want next state Q to be 1, then I need D to be 1. And similarly over here for the final 2 rows. Okay, so this follows from the D truth table. let's write out the D truth table. When D is 0, the next state of Q is going to be 0. When D is 1, the next state of Q is going to be 1. It's that simple. So what I can see here is I'm going to look now flip-flop by flip-flop, okay? And I'm going to look at Q2 only. And I'm going to look at this row. And I'm going to say my present state Q2 is 0. I want my next state Q2 to be 0. What should D2 be to make that happen? Because D2 controls the flip-flop whose output is Q2. So I'm going to look over here and I'm going to say that corresponds. So this case where present state Q is 0 and next state Q is 0, that corresponds to this first row here. And I know that D has to be 0. So if I want that to happen, D is going to have to be 0. Now what about over here? So again, I'm just going to go flip-flop by flip-flop. So I'm still looking at Q2, but I'm over here on the second row. And again, I have this condition where present state Q2 is 0, next state Q2 is also 0, which corresponds to this row. And I know that D2 is going to need to be 0 to make that happen. So let's write that. And for the next row, again, I still have that 0, 0 condition. So D2 is going to have to be 0. But look what happens over here. Over here, in this fourth row, I have present state Q2 is equal to 0. Next state Q2 is going to be equal to 1. So that corresponds to this row of my D flip-flop excitation table. And I'm going to need D equal to 1. In general, for D flip-flops, actually, it's pretty simple because the value of D just has to be the value of whatever you want next state Q to be, right? So here I have 0, 0, 0, 1. And over here I also have 0, 0, 0, 1. And in fact, it's not at all dependent on what the previous state of Q was. So, but we're going to go through this logically, and we're not going to take any mental shortcuts. And only when you feel comfortable enough can you take these shortcuts. So we're going to go look again at this row. We're going to see that present state Q is 1. The next state Q is also 1. And again, I have to make sure I'm looking always at the same flip-flop, right? So I'm looking at Q2, present state Q2, next state Q2. What does D2 have to be to make that happen? What does it have to be to make a next state of Q2 equal to 1, given that the previous state was 1, which is right over here? Well, it just has to be 1. Okay, what about here? I have 1 and 1, and actually I have that for the next two rows. So I know that D is also going to have to be 1. And now let's look over here. I have a 1, but I want a 0. That corresponds to this row. So I have a 1. Next state is a 0. It means D is going to need to be 0. 0. And I'm going to do the same for D1. So now I'm looking only at these columns. Q1, present state, Q1, next state, and D1 is what I'm going to fill in, okay? And I'm going to fill it in using the excitation table for a single D flip-flop. So in order to have present state is 0 and the next state I want it to be 0, and in order to have that, well, that's this row over here. So that's a 0. If I have a 0 and I want a 1, that's this row over here. That's a 1. And then over here, if I have a 1 in the present state and I want a 1 in the next state, that's this row over here. So I want a 1 again. Over here in this row, present state is 1, next state is 0. That's this row. And so D should be 0. Over here, present state 0, next state 0, D should be 0. Over on this row, present state is 0, next state is 1, D should be 1. And we have 2 more rows to go. So present state 1, next state 1, D should be 1. Present state 1, next state 0, D should be 0. Okay, and we're going to fill out D0 in the same way. So let's do that. So again, now I'm looking only at present state Q0, next state Q0, and I'm trying to determine this, control input D0. So what does D0 have to be to get this transition? So to go from a 0 to a 1 at the output Q, that's this row, I need D to be 1. To go from 1 to 0, 1, 0, D has to be 0. To go from 0 to 1, D has to be 1. To go from 1 to 0, D has to be 0. To go from 0 to 1, D has to be 1. To go from 1 to 0, D has to be 0. Actually, you can see the pattern here. To go from 0 to 1, D has to be 1. To go from 1 to 0, D has to be 0. Okay, so these are my control inputs. Now what do I do? The excitation table. So I derive the excitation table. Now what do I do? So I have 3 control inputs, D2, D1, and D0. And now I want to derive Boolean expressions expressing these control inputs, each of them, in terms of the present state, Q2, Q1, and Q0. So that's the present counter state. And the way I'm going to do that is the K-maps. So let's draw K-maps. And we'll see where this all is going. So let's get the Boolean expressions. So we'll start off doing a K-map. And the K-map will have as inputs Q2, Q1, and Q0. I'm going to write the gray code. So what I'm doing here is I'm taking this column and I'm trying to derive an expression for D2 in terms of the present state, Q2, Q1, and Q0, not the next state, the present state. So what do I get? So I'm going to read off the column under D2, and I get 0, 0, 0, 1, 1, 1, 1, 0. And I can group some terms. And get an expression for D2 equal to Q2 bar or Q2 Q1 bar or Q2 bar Q1 Q0. And this actually reduces to a formula, but I'm not going to get into it now. Maybe you'll see it in an assignment later. D1. Let's do D1 now. So what I'm looking at for D1 is this column over here. And I'm going to fill in my K-map. So I have 0, 1, 1, 0, 0, 1, 1, 0. And I'm going to group some terms. And I'm going to get Q1, Q0 bar, or Q1 bar, Q0. And actually that simplifies to this expression over here. Q1 XORed with Q0. What about D0? So D0 is this column over here. I'm going to fill in my K-map. 1, 0, 1, 0, 1, 0, 1, 0. I can group these all together and it simplifies simply to this. D0 is equal to Q0 bar. Okay, that's pretty easy. So now what I'm going to do is I'm going to draw my schematic. So now let's see how this actually applies in practice. How am I going to build my counter? So first of all, we've agreed that we need 3 flip-flops, and those were the flip-flops corresponding to D2, Q2, D1, Q1, and D0, Q0. So let's go ahead and draw the 3 flip-flops. But here's where things start to get different from how they were with ripple counters. So the first thing to note is that for D flip-flops, it does not matter, and for synchronous counters in general, actually, it doesn't matter if I have positive edge triggering or negative edge triggering. The synchronous counter simply doesn't care. Now that was very different than in the ripple counter, where having a positive edge trigger versus a negative edge trigger made the difference whether you were counting up or counting down. But in the synchronous counter, there is no such distinction. So I'm just going to make these D flip-flops arbitrarily. They are going to be positive edge triggered. Now the next difference was in asynchronous counters. So of course the whole reason we called them asynchronous was because each flip-flop had a different clock signal. But these guys are all going to have the same clock signal. So they're all clocked by the same clock signal. Now what I have not indicated, which I will right now, is that the asynchronous inputs are all going to be wired high or inactive. And why is that? It's just because I want fully synchronous operation. So for fully synchronous operation, my asynchronous inputs need to be inactive. And the next change that I'm going to make is, so one confusing thing about ripple counters was that even though when I write out a binary digit, my most significant bit is always on the left and my least significant bit is always on the right. That's just convention. But when I drew the schematic for my ripple counters, I put the least significant, or the flip-flop corresponding to the least significant bit, all the way on the left, and the most significant bit was on the right. So I reversed the bit order visually in this schematic. And why did I do that? I just did that because it was easier to wire. But I don't have that problem here with synchronous counters. So I'm going to go ahead and I'm going to restore rightness to the universe, and I am going to put the most significant bit, or the flip-flop corresponding to the most significant bit, on the left. LSB goes back to its place all the way on the right. So this flip-flop over here, this input becomes D2, this is Q2, and Q2 bar, and this one is D1, this one is Q1, and this one is Q1 bar, and here I have D0, Q0, Q0 bar. And now I'm going to implement my Boolean expressions. So I'm going to write the corresponding schematic. So I'm going to start with D2, which is by far the most complicated one, right? So that's this one over here. So I have 3 product terms. So I'm going to put 3 AND gates. Because it's 3 input. The input to the first AND gate is Q2, Q0 bar. So where do I get Q2 and Q0 bar from? So here's my Q2 output, and here's Q0 bar. Oops, that was a mistake. Put the bar on top of Q0. So you shouldn't have any inverters here at your inputs to your AND gates because you have the flip-flop itself already provides you with the inverted output over here. So you don't need that additional inverter. So if you're asked for Q0 bar, you can just take it from here. You don't have to take Q0 and then invert it. And second AND gate, the inputs are Q2 and Q1 bar. Getting Q2 and Q1 bar from, Q2 comes from here, Q1 bar comes from here. And the third AND gate is a 3 input AND gate. And that 3 input AND gate has Q2 bar, Q1, and Q0. And they go through an OR, 3 input OR gate, and the output of this 3 input OR gate simply goes to D2. So I just implemented this Boolean expression over here. Okay, for D1, now I could implement this expression here, sum of product, but I am going to use the XOR because that just requires me to have one gate. Inputs are Q1 and Q0, and the output is simply and then over here for Q0, well, that's easy. It's wired in toggle mode. And that makes sense because, in fact, when I look at the control input, I can see that, in fact, it is toggling at every clock edge. So this is my full schematic. I have just implemented my my mod-8 up counter using D flip-flops. Now, what do we want to say about this? So first thing is I want to show you how this works at a high level. I sort of want to zoom out at a very high level and see how it works. So I'm going to draw this box around all these logic gates. And I'm going to call this box the control logic. Okay, so this represents the control logic that controls the control inputs for the flip-flops. And over here, this is what I call my memory. So my memory are simply the flip-flops. They retain the state information. So I'm going to visually draw out a block diagram. We're going to use these a lot, so especially when things get more complex. It's kind of useful to sort of conceptually zoom out and see what's going on. So over here, I'm going to draw a box. And inside this box, I'm sticking all my flip-flops. And I'm going to label this box memory flip-flops over here. And the outputs of my box are simply the flip-flop outputs, Q3, Q2. Actually, that would be Q2 and Q0. And the inputs to this box are simply my D inputs, D2, D1, D0. Of course, I've simplified because wherever I write Q2, I also mean Q2 bar. And whenever I say Q1, I mean Q1 bar, and Q0 also includes Q0 bar. But I'm not going to write them. So separately up here, I also have my control logic. And this was the result of those Boolean expressions. And this is in fact Q2, Q1, and Q0 are in fact my counter output. So it's the output of my system in this case because I'm just building a mod-8 counter. But separately, taking the present state Q3, Q2, Q2, Q1, and Q0, and I'm inputting it into that control logic, all those gates that I had from earlier. And out of this control logic comes D2, D1, and D0, like so. And one other thing I forgot is the memory, or one important thing I should add here. The memory, it does have one other input that is not an input to the control logic, and that is simply the clock. So the clock is an input to memory. So if you find this confusing, that's okay. We're going to revisit it over and over, and you will become very familiar with it. So going back to look here, I see that all this is that control logic. The inputs to my control logic are all the Q values and Q bar values, and the outputs are simply D, the D inputs of the flip-flops. And separately here, I have my flip-flops, and the inputs to my flip-flops are the clock, all the D inputs coming from my control logic, and I'm outputting the counter states, all the Qs. And that is it.